And we went through the structures for the mechanism for immune inflammation. We had this discussion about the pH dependence of the reaction. And then we mentioned in the end about how if you can form stereoisomers, indeed you will. So if you have two different R groups on your ketone or aldehyde here, you'll notice if you, with your nitrogen nucleophile, this primary amine, we can form either the E or the Z structure. And maybe we'll come back to it later on after our exam. One of the things, if you're interested in it, with these nitrogen nucleophiles and the imines formation, what's really interesting for those who like biology and biochemistry, is this. You can imagine this being a side chain of lysine, and so there's a lot of biochemistry that goes on with lysine as a primary amine. So let's briefly mention a couple of the other sorts of primary amines one might see. So rather than having this alkyl amine, you could take this. We'll use our same standard acetone here, and let's react this with something that looks like this. And we're not going to go through the mechanisms here because they're the same as what we've seen before. So here we have a compound that's known, it has a hydroxyl group on it, and an amine, so it's known as a hydroxylamine. And what you find is actually that the amino side is more nucleophilic than the hydroxyl group. Nitrogen is going to be more nucleophilic. So you end up forming a species that looks like this. So the same idea as the imine, but now this is known as an oxime. And we'll just cover two of them. These are also useful for historical purposes. That's one. Another one is, rather than having OH NH2, you can have NH2 NH2. So this species here, this compound NH2 NH2 is known as hydrazine, and this is going to generate an imine compound that looks like this, NH2, and hydrazine makes a hydrazone. And so all of these, there are other types of primary amines that could be used. These two products, an oxime or a hydrazone, are useful for a variety of other reactions. That's zone, Z-O-N-E. And just to mention one of the other useful reactions, we'll consider one that you have with this hydrazone here. And I think it's because it falls in line with, it's useful to say, I should say, because it falls in line with other things we've seen recently. So previously, if we wanted to get rid of a carbonyl group, this is useful for synthesis, we have two ways to do this. And I'll write it here because, in case people are still writing down the hydrazone. So I'll say, rather than get rid of, remove a carbonyl group, our double bond O group. We had the zinc-mercury conditions with HCl, so-called Clemmensen reduction. We had the thiol version of this here, thioacetal, followed by, so that's A. B was rainy nickel. And so what you notice here is we have acidic reaction conditions. This is neutral with this thioacetal. And then we actually have method 3, which is known here as the Wolff-Kishner reaction. Or Wolff-Kishner reduction. And I'll just put the name here because I didn't squeeze in all of the reagents. And this is a 2-step process to get rid of a carbonyl group. And what we can do is you'd see that if you had a structure here, let's now fill this in. Say I have this cyclohexanone here that has a carbonyl group on it. And I would like to remove this carbonyl group for some reason. Let's just generate cyclohexane. Now we could do this with zinc and acid, but let's say you don't have those reagents around and you don't want to work with the zinc, mercury, and alcohol. We could do this also here, make the thioacetal. So thioacetal here, treated with rainy nickel, but let's say this reagent's not available. However, the third way to do it is a two-step process where we can first take and turn this ketone into the hydrazone. So we'll take hydrazine, NH2, NH2. We can do this with a little bit of acid, slightly lower pH. This makes this hydrazone here by the same mechanism that we saw yesterday. And then in the presence of strong base and water and heat, so pretty vigorous conditions, you can actually turn this hydrazone into an alkane. So that gives us our third way to remove a carbonyl group. And really why it's interesting is it's one here is acidic conditions, two is neutral conditions, three is it's under basic conditions, so potassium hydroxide. I don't want us to memorize this mechanism, but just to go through it briefly to show something that now all of a sudden we see something that looks quite different. We're losing this whole hydrazone part of the molecule, ending up with an alkane. Seems quite different from anything that we've seen before, but let's see if what we've learned so far we can apply. And what kind of helps give it away is that we're also going to release nitrogen. So that's where those nitrogens are going. So we're releasing nitrogen stable as nitrogen gas. Let's redraw the hydrazone here and expand this part of it. And really what's going to happen is a lot of acid-base chemistry. So we have a strong base around with potassium hydroxide. So what we can do is think about deprotonating this nitrogen. This is not a very acidic proton. This is why we need the strong base and heat. So occasionally we're going to end up deprotonating. Now what we have is we first started with the neutral nitrogen. Now we have a negative formal charge on that nitrogen. And also using this now, I mean, normally in a class I would pause and we would write resonance structures, but we'll just do it here. We could write a resonance structure. So they remove these electrons to form a nitrogen-nitrogen double bond and move these electrons down into this carbon. Draw it large enough here so we have this. And now let's just put it over here. So this is a resonance stabilized species. And what I haven't quite shown yet is that we're going to generate water with hydroxide pulling this proton off. Now we have water around. Let's just put it up on top here. So that can quite readily get protonated, it meaning the carbon here. Let's take a proton off and we're going to regenerate our hydroxide. This is really not going to be reversible. So now we have all of this is the same. And it looks like we put one hydrogen here. So we're halfway there. We want to have two hydrogens here on this carbon as our cyclohexane in the end. We have one of them there. Well, let's just try doing the same thing again. Have hydroxide around. Let's go ahead and take off this other proton here. And why don't I fill in the lone pairs of electrons? We start off with one lone pair, and then we're going to end up with a second lone pair. I'll scroll down just a bit. So now what we end up having is this nitrogen, two lone pairs of electrons. It has a negative formal charge. I'll put this hydrogen in here just to highlight it, but it's still there. Plus we've generated water. I saw a message there. Are other people having problems connecting here? No. So if you miss something, Paul, let me know. Others are good. Okay. It looks like it might be your connection, Paul. So just let me know if you have any problems, if you miss something here. Okay. Others are good. So now what we're going to do is we have this here, nitrogen, the double bond, looks a lot or close to N2, which would be very stable and energetically favorable to form. So let's just move these electrons here to form the nitrogen triple bond. We'll break this carbon-nitrogen bond, put those electrons under the carbon. Put this hydrogen here, negative charge. Oops. carbon, we've released this. We can put the lone pair here. Uh-oh, what happened here? There we go. And then in the last step, we're going to regenerate our base to form our alkane in the end. Put that there for emphasis. Plus hydroxide. Okay. I know there's different ways of making internet connections, and sometimes better than others, which might help. So for this mechanism here, again, don't memorize this, but the idea is to see that something that looks a little bit different than what we've seen. Now, we could draw the mechanism for formation of the hydrazone based on our discussion yesterday. And now we see that once we form the hydrazone in a strong base with heat, we end up with this cyclohexane. Nitrogen is released, and it brings back some ideas of acid-base chemistry. It's a little bit different than what we've seen. Resonance, and then formation of nitrogen in the end, which is going to be the driving force. So this is a useful reaction for removing a carbonyl group. So that's our third way now of removing a carbonyl group.